The ignition system used in today's vehicles is only part of the engine management system. The ECM controls all the functions of the ignition system in response to inputs from a variety of sensors. Many of the inputs used in the ignition control are used in other vehicle systems as well. The electronic ignition systems currently available to manufacturers range from distributor-based, distributorless, wasted spark to coil overplug. They may have different components, but they all operate using the same principles. The best way to understand an ignition system is to go back to the beginning and review a contact breaker or Kettering system. There are two parts to all ignition systems: low tension or primary, and the high tension or secondary. The ignition coil houses both a primary and secondary circuit. Current from the ignition circuit flows through the primary coil to ground via a closed set of contact breakers. The primary coil is formed from around 300 turns of coarse enamel-coated copper wire. As the current flows through the circuit, a strong electromagnetic field, or flux, is created around the winding. When the contact breakers are open, there is no current flow in the circuit, so any magnetic flux formed will collapse and dissipate. A ballast resistor may be used in the primary circuit to fulfil two purposes. The main reason is to reduce the current flow to the primary windings to help increase the magnetic flux saturation. By reducing the current the coil needs to produce a magnetic field, we can reduce any back EMF created. With a lower back EMF, greater coil saturation is achieved. A second reason for using a ballast resistor is to aid in cold engine starts. Under cranking conditions, the available ignition voltage drops to around 10 volts. If an ignition coil was designed to operate between 12 and 14 volts, this cranking voltage supply would limit the output of the ignition coil when it's needed most. By designing the coil to operate between 8 and 11 volts, the coil is able to produce its full output even under cranking conditions. In this design, the ballast resistor is bypassed during crank conditions. The contact breaker set, or points, is in reality just a mechanical switch. They are only there to turn the primary current on and off. The contact set is designed to be opened by a cam lobe when mounted in a distributor. A 4-cylinder engine would have 4 distributor cam lobes, one for each cylinder. The distributor is connected to the engine crankshaft or camshaft and is geared to turn at half crank speed. This distributor cam lobe opens the points via a follower block 4 times per engine cycle. The contact set needs to be adjusted to a minimum clearance. This ensures the air gap is great enough to inhibit current flow across the contacts. When the points close, current again passes through. The longer the points are closed, the more time is given to coil saturation. We refer to the close time of the points as the dwell angle. The dwell angle for a 4-cylinder is typically about 60 degrees. This is the number of degrees of distributor rotation while the contacts are closed. The time the points are closed, or dwell, equates to the saturation time of the primary windings. The longer the contacts are closed, the stronger the magnetic field created. The current flow through most primary windings varies with supply voltage and coil resistance. It can be anywhere between 3 and 9 amps. When the contact set starts to open, a high current will continue to flow across the air gap until the resistance becomes too great. This continuous current flow opposes the collapse of the magnetic field in the primary windings and causes oxidising and burning of the contact set. To help speed up the collapse of the magnetic field, we need to stop the current flow across the contacts as soon as they are open. This is done with the use of a capacitor, or more commonly called a condenser, mounted in parallel with the contact set. As we know, electricity can be a bit lazy. With a capacitor in the circuit, the current has an alternate path to travel, rather than jump the high resistance air gap. The secondary circuit consists of an ignition coil, high tension leads, distributor cap, rotor, and spark plugs. The ignition coil houses another winding with about 20,000 turns of very fine enamel-coated copper wire. One end of this copper wire is connected to the primary positive connection, and the other end connects to the high voltage output terminal. A high tension lead connects the coil to a distributor cap. The design of an ignition coil puts the primary and secondary windings in very close proximity, but they are separated by an insulating material. When current flows through the primary windings, a magnetic flux is created and expands across the secondary windings. By placing a ferromagnetic material, such as soft iron, in very close proximity to the primary and secondary windings, the magnetic flux can be concentrated around the windings. This ferromagnetic material provides an easier path for the magnetic flux to follow. The concentrated field allows for complete saturation of the secondary windings, and therefore higher voltage when the field collapses. As the contacts open, the collapsing flux induces current flow in the secondary windings. This is stated in Faraday's law of mutual induction. Because of the difference in the ratio of windings between the primary and secondary circuits, the voltage induced in the secondary circuit will be reflected by this ratio. An ignition coil is a step-up transformer. It uses a small voltage with high current to produce a high voltage with a lower current. Early ignition coils were manufactured in a tubular shape with the windings surrounding the iron core. The assembly is immersed in oil to aid cooling and provide additional electrical insulation. The amount of available voltage the coil will produce is totally dependent on the resistance of the air gap at the spark plug. The more resistance the spark encounters at this air gap, the more energy is required to breach the gap. With the coil acting on the spark plug under atmospheric pressure, it will only generate a couple of 100 volts. This is all that's required to jump the air gap under these conditions. As the resistance of the gap increases, the energy needed to arc across the air gap must also increase. An engine operating at idle speed requires around 10 to 12 kilovolts to overcome the plug gap resistance, while an engine operating under full load may require around 20 kilovolts. This resistance change is because of different fuel mixtures and cylinder pressures under different operating conditions. All ignition coils are designed to operate well below their peak output. The normal operating range for an ignition coil may be between 5 and 15 kilovolts, with a peak output of around 25 kilovolts. This means we have a reserve voltage of around 10 kilovolts. This is needed for when a sudden change in cylinder pressure requires a momentary increase in coil output. Ignition coils are not designed to operate at peak load for extended periods. Coil failure will occur. When the contact breaker closes and current flows in the primary circuit, the concentrated magnetic flux influences not just the secondary windings, but also the primary. This is called self-induced EMF. As the contact set opens, the magnetic field collapses through both windings. The induced voltage in the secondary winding exits the ignition coil to the distributor, while the self-induced voltage is stored in the capacitor. The self-induced EMF can be as high as 400 volts and may influence the primary windings for the next saturation period. When the points close, any residual voltage will exit the capacitor and discharge to ground. The distributor contains the secondary distribution circuit, the primary switching circuit, and the advanced mechanisms. After the secondary voltage leaves the ignition coil, it's delivered to the centre terminal of the distributor cap via a flexible high-tension lead. It's transferred through a spring-mounted carbon brush to the revolving rotor arm, or button. This button has a brass conductor along its surface. The rotor button is attached to one end of the distributor shaft, with the other geared to either the cam or crankshaft. When the button is adjacent to the appropriate fixed outer electrode in the distributor cap, a high voltage charge will jump the air gap. Each terminal is connected to a high tension flexible lead that conveys the current to each spark plug. The opening of the contact breaker is timed to the position of the rotor button. The rotation of the distributor shaft and the discharge of energy to each terminal of the distributor cap must correlate with the engine's firing order. One of the main reasons we have phased out contact breaker ignition systems is due to their reliability. A contact set, being a mechanical device, is subject to wear and tear. They use a distributor cam to open and are closed via a spring, manufactured as part of the contact assembly. In a 4-cylinder engine, a contact set opens and closes twice each engine revolution. An engine idling at 1,000 revolutions per minute has to open and close the contact set 2,000 times in 60 seconds. And the same engine spinning at 8,000 revolutions a minute requires the points to open and close 16,000 times in 60 seconds. This equates to a charge and discharge of about 4 milliseconds. The more cylinders an engine has, the less coil saturation time is available for a given RPM. At these high engine revolutions, the mechanical contact set may suffer from point bounce. This is because the distributor cam is spinning so fast there is no time for the points to close to initiate coil saturation. The rubbing block tends to float between the two high points. Without the points closing, an ignition misfire will occur. This short dwell time can be improved with the use of a twin contact breaker system. Contact sets generally have a lifespan of about 5,000 kilometres. Although not difficult to replace, car owners often neglect this task and are left stranded on the side of the road. If the ignition is left in the on position for any length of time and the contact set is closed, the current draw through the primary windings may be enough to overheat and damage the coil assembly. Contact breaker ignition. It's an old system, but it was instrumental in the development of current ignition technology. The latest ignition systems are very different, but still use the basic principles of mutual induction. By understanding these principles, diagnosing modern ignition systems will be a lot easier. Thanks for watching.